Hi, this video is on mass spectrometry, which we did meet in an earlier topic when the purpose of studying mass spectrometry was to work out the ARs of elements from the isotopic mass numbers. But in this case, we're going to look at putting organic molecules through mass spectrometers and have a look at identifying such molecules. So first of all, let's have a look at a few pictures as to what we might use a mass spectrometer for. This is a picture of a Roman gladiator, and even in those days, 2,000 years ago, the gladiators would take nutritional supplements like herbal extracts in those days to improve their performance. Of course, nowadays athletes take anabolic steroids and their urine samples need to be analysed. And here would be a bunch of urine samples on their way into probably a gas chromatograph to be separated. So the gas chromatography equipment would separate the organic molecules within the urine sample, and those organic molecules would be fed directly into a mass spectrometer from which they would be identified. Also, what we have here is a diamond. Using a mass spectrometer, you can work out exactly where in the world the diamond comes from, and that aids illegal trade in diamonds, or leads to the identification of the illegal trade in diamonds. What's more, water samples are routinely taken and analysed for organic substances that shouldn't be in our samples, drinking water. And lastly, let's have a look at this 2,000-year-old Mayan pot. And interestingly, what scientists were able to do with this pot is examine what it was used for. And this pot from 2,000 years ago is probably the earliest known use of cocoa for chocolate. And it was also established that the chocolate contained other ingredients like chili. So there's a few uses of mass spectrometry, and let's have a look now at what we need to learn for our spec. So we've got a couple of lesson objectives. First of all, we want to be able to find the relative molecular masses of organic molecules. And lastly, we want to have a look at high resolution mass spectrometry. That just means a little bit more precise measurements, and we're going to have a look at those two things. So first of all, finding relative molecular masses and identifying certain compounds. We might have a mass spectrum, and we'd look at that mass spectrum. You might also know that the spectrum is of a straight chain alkane, as in this question. And it's going to contain a molecular ion, because you'll remember that what happens is the sample gets bombarded by electrons to make a positive ion, or potential differences used to make the molecular ion, and it's going to have a peak, and that peak in this case is 72, and from that peak of 72 that we get from the spectrum, we need to identify the compound. So here might be that spectrum, and the MZ is the x-axis along the bottom, and you can see a bunch of lines that have different relative intensities at various values of MZ. So what we want to do to identify the molecular ion is to find the peak with the largest MZ value, and that in this case is this one here. So it's the largest MZ value, not the highest intensity peak, which would be this one, of course. So the peak with the highest MZ value, and Z is pretty much always 1, where Z equals 1. When Z equals 1, then M over Z equals M. So what we can say is that the M value here, which is 72, all right, is the MR of the compound. Okay, so from this spectrum we read that the MR is 72, the biggest one is always the molecular ion, and all these other ones here, the ones with smaller MZ values, are the fragments of that ion as it gets broken down, either by bombardment or just because the molecular ion, when it's a positive ion, is unstable and breaks down. So there we have it. We have the MR equals 72. What is the compound? And in this case, we're going to work it out by trial and error. So we know that we've got a straight chain alkane. So the first of which is methane. The second one is going to be ethane. The third one is going to be propane. Fourth one would be butane. And the fifth one, and the fifth one is going to be pentane. Okay, and sixth one would be hexane, etc. Okay, so it's going to be one of these, but the MR is going to be 72. So clearly we can see it's not going to be methane because carbon is 12 and we've got 4 hydrogens, so that would be 16. So it's quite a bit bigger than methane. Let's try at the bottom one, pentane. So we've got 1, 2, 3, 4, 5 carbons, so 5 times 12 is 60. Right, how many carbons we've got, how many hydrogens we've got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus 12 equals 72. And so our 72 here matches this 72 here. And so therefore we have identified this compound as being pentane. Okay, that's a simple sort of problem that you might get in this topic. Let's have a look at a different sort of problem you might get. And in order to do that, let's introduce this high resolution mass spectrometry, which is just more decimal places. So more decimal places to our data, often 4 decimal places. So let's have a look at it with an example. Let's say, for example, we have propane. Propane is C3H8, and let's say we have another compound. Let's call that ethanol. Okay, so ethanol is CH3, CHO, and let's look at our MRs of these two compounds. So 3 12s, working out propane first. 3 12s, 36. 36 plus 8 is 44. Okay, let's do the same for ethanol. We've got 12 plus 3 equals 15, plus 12 is 27, 28, plus 16 is 44 as well. So they're both 44. So if we had a low resolution mass spectrometer that just gave us our MRs to 0 decimal places, then it couldn't distinguish between those two products. So that's why we have high resolution mass spectrometers. Let's have a look at an example to illustrate it. Okay, so we've got a high resolution mass spectrum. That's the graph. And we've got a compound that has a molecular ion with MZ 98.0336. All right, now we need to work out its molecular formula. We're given a bunch of options. It could be one of these 4 options. So how are we going to work out which one it is? Because they're all pretty close to 98. Well, what we have to do is we have to work through them one by one. But we need the data first. So for hydrogen, we know it's 1.0078 to those 4 decimal places. And we're given carbon 12, nitrogen and oxygen as well. Okay, so for A, we're just going to work out A. first. So we've got 5 carbons, that would be 5 times 12. And you should really do 5 point, write down all your decimal places each time. Okay, so, and we've got 10 hydrogens. So it'd be 10 times our 1.0078, and it'd be 2 times our nitrogen, which is 14.0031. And right, you do that calculation, it comes out to be 98.0842, which is not quite close enough to our 98.0336, so we know it's not going to be A. And I tell you what, I'll leave you to do B and C. Let's work out D. D, we have C5H6O2. So that is 5 times 12 exactly again, plus 6 times our hydrogen, and 2 times our oxygen. Right, when you do that calculation, you come out with exactly the right answer, or exactly the answer we need. So it's 98.0336. And so you know that this compound that we had in the high resolution mass spectrometer is D. And so there you have it. Okay, let's look at a potential exam question. So here we have a student runs low resolution mass spectrometry on a sample of a compound which he or she knows is either C3H6O, looks like a ketone, C3H8N, looks like a amine, C4H10, looks like an alkene. Not that we need to know that in this case for this question, because the question is, why might low resolution mass spectrometry not be able to distinguish between these molecules? Well, let's work the MRs out for each one. So C3H6O, the MR is going to be 3 times 12 plus 6 times 1 plus 16, and that's going to equal 58. Our C3H8N, our MR there is going to be 3 12s again, 8 1s, and a nitrogen, and that comes out at 58 as well. And guess what the next one's going to come out at? C4H10. Let's go through the process. MR equals 4 times 12, 48, plus 10 is 58. So they're all equal to 58 if our resolution is just to no decimal places. So the second part to the question might be, the sample is injected instead into a high resolution mass spectrometer. The molecular ion peak, remember that's the one on the right hand side of the spectrum. The MZ value is 58.0655. Alright, so now we've got 4 decimal places instead of none. And what's the molecular formula of the compound? Alright, so we're going to do exactly the same thing. So the MR of C3H6O, using the accurate data, is going to be 3 times 12.0000 plus 6 times 1.0078 plus R 15.9949, and that's going to come out to be 58.0417, which is not quite close enough to our 58.0655. So we have to do the same for the next compound, which is C3H8N this time. Alright, so we're going to do 3 times 12.0000 plus our 8 times 1.0078 plus nitrogen is 14.0031. And we plug that into our calculator. And it's coming out at, hey presto, 58.0655. So, which is the same as the mass spectrum. And so we know that the formula is C3H8N. That's the answer to that question. Let's try another potential exam question. Here we've got a mixture of 2 compounds, and it was analysed in a high resolution time of flight mass spectrometer. Right, the sample produced the 2 molecular ion peaks shown on the spectrum below. Okay, so we've got one at 88.0085 and one at 86.1092. And the question, so the mixture consists of 2 of the compounds listed below. Okay, so we don't know which 2, we're given 4. Using the precise atomic masses given in question 1. So here they are, we give you those. Work out which of the 2 compounds makes up the mixture. So we're going to do the same thing as we did in the previous question. We're going to hope that one of the MRs that we work out for these 4 compounds turns out to be 86.1092, and another one comes out at 88.0885. So let's just crack on. We might as well start with butanoic acid at the start. So butanoic acid, 4 carbons. So we're going to have let's call butanoic. Let's just write it out. Butanoic acid. Okay. So they're going to be MR equals our 4 times 12. Oops, 4 times 12 point all the zeros plus our, how many hydrogens have we got? We've got 8 hydrogens. Our hydrogen is 1.0078, and we've got 2 oxygens. So when we add those all up together, we're going to get 88.0522. Which is not one of either this one or this one. So that means we have to carry on. Pentan 1-ol. Let's change colour just. Pentan 1-ol. So the MR is going to be 5 times 12, 5 carbons, plus our 12 hydrogens, and what else have we got? 1 oxygen, so that's 15.9949. Okay, so let's add those all up, and we get 88.0885, which is this one here. So this peak here is for pentan 1-ol. And if you did the same thing for pentan 3-ol and hexane, you would find out that the MR of hexane The MR of hexane turns out to be 86.1092. So we know that the other molecular ion peak, this one here, is for hexane. Okay, so that's it for this lesson. Quite a quick and simple lesson. I think the only tricky thing to remember is the molecular ion peak is the one on the right hand side, the one with the largest MZ value. That's the molecular ion peak, and all the other peaks to the left of it are either fragments of the molecule or include different isotopes of some of the atoms. So there we have it, that's mass spectrometry, and that's introduced you to high resolution mass spectrometry.